So as announced before, Joshua Foster will tell us about simulating post-inflationary misalignment. All yours.
All right, yeah, thanks for bearing with the second talk, everybody. I'm gonna give you a talk about AXIONS. I guess we've already heard one of those, but I'm gonna start out a little more generally and just sort of motivate the picture for AXIONS and the experimental landscape before we really dive in. So like the super naive question we can of course ask with AXIONS is what happens if I put a neutron in an electric field? A more complicated question I can ask is, can I introduce this theta bar GG dual term into my standard model Lagrangian? The answer to the neutron and electric field is it turns out it's not going to precess. Maybe you find that a little weird. And if you think a term like that should appear in your Lagrangian, then you should indeed find it very clear that the neutron doesn't precess, because this term should be given the neutron and electric dipole moment. We go out and we measure that neutron electric dipole moment. We find it's really tiny, and there's an angular parameter associated with our theory that I'm just calling theta bar here that we measure to be less than 1 part in 10 to the 10. But of course, it could have been anywhere between 0 and 2 pi. Now, I don't have a great prior for what value theta bar should take, so I'm just going to pretend that it should be uniform on 0 to 2 pi, in which case I find less than 1 part in 10 to the 10 to be very odd. Now, if you have a really great theory that predicts some prior on theta bar that says it should be less than 1 part in 10 to the 10, we can move on with our lives. But for the meantime, I want to think a little bit about the strong CP problem here. All right, great. So the way we sort of resolve this problem of having a free parameter that could have been any value but took on a really small one is we say there must have been a dynamical reason this was realized in our theory. So what we do is we introduce an axion, and it's going to couple to this GG dual term, just like our theta bar did. So now we can think of this as having an effective theta bar, and it looks like theta bar plus A over FA. So FA is just an energy scale that's associated with the dynamics that are giving us the axion. And the important point here is that we're getting this potential for the axion. So I'm giving it to you in terms of its mass, MA, its decay constant, FA, and now the interesting parts of the potential are this 1 minus cosine of our effective theta angle. The thing that the axion is then going to do for us is it's going to make this effective theta angle dynamical. We're going to be able to minimize our potential, and that's going to be exactly when the effective theta angle is 0. So we've solved our strong CP problem. Now, the particularly exciting thing here is that I've introduced the axion, and that can have some relic abundance, and that could be our dark matter. But that actually doesn't give me too much information about where the axion should be living. So if I think about the viable parameter space for axions in terms of this plot, so what I'm showing you here is on the x-axis, the axion mass, on the y-axis, the axion's coupling to a photon. What we see here in yellow is sort of this well-motivated QCD axion line where we get to solve the strong CP problem. There are a lot of colorful constraints indicated on here, but I think the most striking feature of this plot is just all the white space. So there's a lot of parameter space where we could have axions or axion-like particles, and we haven't even gotten there yet. So I want to focus in a little bit on a class of experiments called haloscopes. So I've circled them here. And these haloscopes are looking for axions or axion-like particles that are also the dark matter. And there's an increasingly mature haloscope program. So the ADMX experiment has been running for a long time, but now we're getting Haystack and CAP and a number of others like MadMax and the proposed plasma haloscope. And really, right now, these are the experiments that are coming the closest to probing this yellow QCD axion band. But I also want to tell you that these experiments, as good as they are actually sort of undersold by that plot. And the reason is all of these experiments are employing a resonance scanning strategy. So what they do is they look for an axion that's associated with some frequency. They tune a resonator to that frequency. They make a measurement. They say, I did find the axion, or I didn't find the axion. And assuming they didn't find the axion, they keep stepping through the frequency space that they're sensitive to. What this means is only a small fraction of your time is dedicated to looking for any particular axion mass. So the alternative is you could say, I really believe my axion should have this particular mass, and I'm going to spend all of my time with my resonant experiment looking at that mass, and I'm going to have really great sensitivity. So in practice, those experiments are secretly 2 orders of magnitude more sensitive than are being shown. You lose that 2 orders of magnitude in sensitivity to a particular axion mass when you implement a scanning strategy. Great. So it would be really great to have this axion mass in mind. So we could say, if you have a QCD axion and it is the dark matter, this is its exact mass, and this is where you should tune all of your experiments. And what we need to do is think a little bit about how we can do a theory calculation that might tell us precisely what that mass is. So in thinking about that, we need to think about how we realize axions in the early universe and whether or not they give us a predictive power. So I want to think about axions as they arise from a spontaneous symmetry breaking in the early universe. And I'm going to call this scenario misalignment. So there's sort of two regimes we care about. There's pre-inflationary misalignment. So we get the axion before the end of inflation. That's the scenario shown on the left here. What happens is the axion gets a random value. So much like theta bar, it just acts like a phase. So the axion is going to take on a random value between 0 and 2 pi. It can take on whatever value it wants, but I only get one draw from it because then inflation is going to blow up the causal horizon, and I'm only going to see a homogeneous field inside my observable universe today. And that means that just like theta bar is a free parameter, so too is the initial condition for the axion field. So unfortunately, I don't actually have any predictive power in this scenario because I can tune theta to be as small as I want it to be, or as close to 2 pi as I want it to be, where I get the benefit of some anharmonic effects to make really any axion mass viable. The more interesting scenario at a predictive level is the post-inflationary misalignment scenario. What happens here is the axion gets produced shortly, or well, sometime after the end of inflation. What that means is the causal horizon then is much smaller than the causal horizon is today. That means on each independent Hubble patch, we're going to pick a random value of the field, and we're actually going to get like huge statistical precision. You're going to have something like 10 to the 60 draws of the axion field in the observable universe today. So there's no scatter in the average of 10 to the 60 things. So I can sort of say in this scenario, I would say my axion abundance is basically going to be the initial field value, the one single initial field value, and then my F is going to sort of evolve that initial value down to the present day. But in the predictive post-inflationary scenario, I'm going to have to average over all of my initial field values and evolve those individual field values down to the present day, and that's what's going to give us the precision to predict the axion mass. Great, so like I was saying, this is just sort of the picture. You have some initial, in the pre-inflationary scenario, some initial misalignment. Eventually your axion starts to oscillate, and then it decays away, and it's these little fluctuations around the VEV that are going to give us the dark matter abundance. And like we've been seeing, this is the scenario we have for post-inflationary misalignment. And if we want to actually think about how we would do that evolution, we might just sit down and write down the equation of motion for an axion. And already you can tell this is going to be a little bit complicated because I have to think about all of these gradient terms that are appearing by merit of having an inhomogeneous field. Great. So that's not really the only complication here. The big difficulty I'm going to have is with topological defects. So what you should have in mind is on each horizon, you get an independent axion field. And if you look at the axion field in some right location, you would notice that the field would wind around between 0 to 2 pi in terms as it goes around the potential. Those locations are called topological defects. And if you think the field is sort of wound around the pole of the potential that it's experiencing, and you can't just pull the string and straighten out the field, you actually have to like roll the field over the top of the potential, which really is to say that although you got the axion out of some spontaneous symmetry breaking, at the location of these topological defects, whatever the UV dynamics were are being restored. You can see this sort of in terms of the very large gradients that you'd measure as you tracked the axion around one of these topological defect locations. So we're going to want to study this. And since I'm telling you we have difficult things like inhomogeneities and topological defects that are going to be nonlinear, what we're just going to have to do is write down a simple effective theory, and we're going to have to study this on the lattice. So here I'm giving you this Lagrangian that's going to realize the axion as the phase of a complex scalar. I'm going to refer to this as a PQ scalar. So just diagrammatically, what I have is I have this PQ kinetic term. I have this PQ complex scalar that's experiencing a quartic potential, but it also has a thermal mass. So at high temperatures, there's a symmetry, this U1 that I need. And then later, as the temperature drops, I'm going to break that U1 and produce my axion. And then at very, very late times, I'm going to have a QCD potential, and that's just going to describe how the axion gets its mass. Cool. So schematically, here's my PQ field. It's sitting in the bottom of its simple quadratic potential when it's dominated by the thermal mass. The temperature drops. Now I have this Mexican hat potential. This axion represents this unconstrained phase, but otherwise the radial mode should be more or less frozen into its VEV. And then at very late times, my axion mass turns on. It's a bias that tilts my potential, and the axion rolls down to its minimum where the effective theta angle is 0. Good. So now we get to some of the more fun parts where I get to show you actual animations of what this looks like. So basically, we take this Lagrangian, we write down some equations of motion, and we put it on the lattice. So this is a result of a simulation where we start at early times where the PQ symmetry is a good symmetry. We evolve through the PQ symmetry breaking, and then we have this initial spectrum of strings in our simulation box. So that's all these little yellow locations that I'm worried you can't see very well, but never mind. As you evolve the string network through the QCD phase transition, you see the network collapses, and you're left with these bright locations where you have high energy density in the axion field. So in principle, this is like what you need to do to predict the axion mass. You should say how much energy is left over in that box after I've gone through all of my complicated dynamics, and then what do I need the axion mass to be to cause that leftover energy density to be the right amount of energy density. And this is something we've done and use these simulations to make a prediction of what the axion mass should be. And just taking that simulation on its own, the prediction is basically for an axion of mass 25 microeV. Now, this is a prediction that's a few years old now, and I'm going to tell you why it might not be the right story anymore, and what you can do to study the more complicated scenario. So what we have to really think about here in these simulations is that we're performing them in a cosmological background. So the scale factor is increasing, and I'm going to be performing this simulation on a co-moving grid. And what that means is, as I advance in time, my pixels are actually getting larger and larger, but that my physical features are staying the same scale. So for example, these strings in my field, the string width is set by the axion decay constant FA, and that number isn't changing in time. So I'm effectively losing resolution of these strings. Well, and I should say also, of course, if you lose resolution in your lattice, then you have a simulation of noise. You don't have a simulation of physics. The other thing that is sort of tricky for these simulations is that you need to, at all times, have multiple Hubble volumes. And the problem is, if you don't have multiple Hubble volumes, you're going to find yourself in a scenario where you have large-scale topological defects that give you finite size effects. You don't want that. That's an unphysical scenario. So there's this difficulty you have in jointly balancing a high-resolution simulation and a high-volume simulation. And when we do these simulations, so for example, the animation I showed you previously, there's like a huge simplification that went into that. You're just saying that the hierarchy of scales between the PQ phase transition and the QCD phase transition was a factor of 10. The results are then extrapolated to try to find what the right PQ scale is. And when you do that extrapolation, you actually get a hierarchy of about 10 to the 11. So that's not even close to being realized in your simulation. And there might be a question of like, are there effects that you're missing by merit of only having this factor of 10 hierarchy that you would have seen if you really had the true hierarchy in your problem and you evolved for the full time scale between the very, very early universe dynamics and the very relatively later dynamics in the QCD phase transition. And there's a possible hint from the string tension. So a quantity that you can go compute is what is the amount of energy density per unit length that these strings are carrying. And if you do that calculation, what you find is that it depends on the log of the ratio of the radial mode mass to the value of Hubble at the time that you're looking. Of course, Hubble is evolving as you advance in time, so the string tension is evolving as well. So even though we thought we had sort of simple dynamics, what we're seeing is that there are interesting features of our problem that are evolving, and maybe the string tension is not the only one. So this brings us to some results that are found by Marco Gorgetto and Giovanni Villadoro and Ed Hardy, who found that if you measure the string length per unit volume in your simulation, that quantity appears to be growing. You might not have expected that, and prior to these findings, the generic expectation is that you'd always have about one string per Hubble. So now that you see that this quantity is growing, this is even more hints of dynamics that are evolving with time, and that you would see have larger and larger effects as you realize a more accurate hierarchy between PQ and QCD in your simulations. Now, this is particularly interesting because these strings can actually radiate off axions. So if you have more strings, you can just radiate off more axions. And maybe the string production starts to matter in comparison to the normal misalignment story that people like myself were calculating. At the very least, what you need is you need to understand what the string spectrum should be around the time of the QCD phase transition so that you can have a realistic simulation of the QCD phase transition with the right initial conditions. Great. But another really interesting quantity to go measure in your simulation is what does the spectrum of axions emitted by strings look like? And the reason you care about this is when these strings are radiating off axions, the axions are massless. So you can either emit into the UV, in which case you're producing not very many axions, but they have lots and lots of energy. But of course, they're going to redshift and not represent an appreciable contribution at late times. Or you could produce a very, very large number density of IR axions. And then when the axion acquires its mass, those could represent an appreciable contribution to the relic abundance today. So the question here is, does the string emission go into sufficiently IR modes to be noticeable in our calculation? And at the scales that can be simulated right now, the answer is no. But again, thanks to Marco and Giovanni, we have some simulations that say, although initially the emission is UV dominated, it is trending towards IR dominated. And if you extrapolate this spectrum out, you find a very, very IR-dominated emission spectrum at times relevant for the QCD phase transition, which could change your axion relic abundance by several orders of magnitude. So here I'm just giving you a quick depiction of sort of what that looks like. So Q is this index on our emission spectrum. So Q greater than 1 means IR-dominated. Q less than 1 means UV-dominated. And for very large Q, so like infinity or for 2, what you should then do is you should compare to this black dashed line, which is sort of the misalignment contribution. And you would then notice that at logs of like 16 for MR over H, that Q equals infinity is outproducing misalignment by quite a bit. But also, it seems like the right scales that you need to evolve to or extrapolate out to at least are logs equal to something like 60 or 70. So even this is underselling the story, but it's telling you that it's certainly possible that strings could outproduce misalignment. On the other hand, if Q stays less than 1, so you can look at here where it's like 0.8 or 0.7, then the string emission never really is competitive with misalignment. So this is certainly something that could change our calculation of the axion relic abundance, but it's a little unsatisfying that we don't actually see the spectrum transition into IR domination. We just see maybe some trends. And it'd be really, really nice to do simulations that get to larger values of the log and really see how this emission spectrum is evolving. Yep. What sets Q? What sets Q? I mean, here, I've just made some choices to illustrate what could happen. These are results from Marco and Giovanni's simulations where they're measuring Q as realized in their simulations.
No, I mean, like, how do you, I mean, it seems like Q is a property of a specific model. Like, what do you change to get a different Q? The mass, is that the statement?
Good. So what's happening is this is like a time parameter. So all this is telling you is that like the strings are doing what they will in your simulation, and it turns out as you go later and later, it seems like the Q is evolving.
Okay, Q is changing with time.
And if Q is evolving, I don't have a good theory explanation for why it is. It's just right now on some level like what you pull out of your simulations.
Okay, thank you.
Great. So the point here is in these simulations that I've been referring to, they've actually totally given up on simulating QCD. They're doing pure string simulations. But even in these simulations, you're fighting your requirements of having a large volume and having a really high spatial resolution. So specifically, these constraints say I need delta x, so the lattice spacing, times the radial mode mass to be less than 1. And I also need the co-moving size of the box times the co-moving Hubble to be larger than 1. And if you put these constraints together, you find that with a very large lattice, so something like 5,000 cubed lattice sites, that you can only get to log of about 8, which is not what you wanted if you said, I think the physical hierarchy is at log equals 7. In any case, I want to tell you a little bit about how you can get past log of 8, although certainly not that close to log equals 70. And the trick here is with an approach called adaptive mesh refinement. So adaptive mesh refinement is a technique for solving partial differential equations on the lattice. And the idea here is you have a system where on small scales, on isolated locations, there are interesting dynamics at small scales in your box. But at most locations, your box is smooth and you don't need very, very good resolution. And that's exactly what you have in this string scenario. You have strings that are narrow because they're sort of associated with a UV scale width, but then you have horizons where, other than the strings, things are more or less smooth. So you'd like an algorithm that says, I give you really good resolution of the strings, but I don't waste memory or computing power on having a really high resolution of the rest of your simulation box. That's what adaptive mesh is exactly doing. So here we start out at sort of our refinement level 0, so the coarsest resolution in our lattice, and we've identified a string location, and we say, okay, we need good resolution of that string. So we add a second lattice, and this second lattice sits inside of our coarser one, but it has a higher resolution. So here it's a twofold increase in resolution compared to the coarser level. And we say, oh, well, that still doesn't give us good enough string resolution. So let's add a second refinement level sitting inside of the first refinement level. And now what we've done is we've gotten 4 times better resolution, but again, we're only applying it at the location of the string rather than applying it everywhere in a uniform lattice. So now I want to show you sort of, yeah.
What happens once the strings they move on your lattice?
Yeah, that's a great question. So the way we implement this, we have a tagging algorithm, which lets us identify the strings. Once we've identified the location of a string, we say you need to resolve that location plus some width around that location. And then you need to recheck where your string is at a time interval corresponding to how wide that padded refined region was divided by the speed of light. So the idea here is that you're setting up a refined box around your strings that are so big that the string can never escape before the next time you're going to check where the strings are and redefine your
so you evolve the whole lattice.
Say that again?
So you evolve the lattice?
Yes, the lattice is, yeah, so that's the adaptive in the mesh refinement. Yeah, the lattice moves around, or the high resolved regions of your lattice move around with the interesting features that appear in your simulation.
Thanks.
Yeah, so this is, yeah, I guess I should say this is sort of different than like, some of the techniques that get used in like n-body, where you say, oh, this was an interesting feature. I'm gonna go back and redo my simulation, but I'm gonna like populate this with like a bunch of smaller test masses. This is really all within the confines of one simulation, and you're just adapting things as you go. Yeah.
The mesh keep track of high frequency modes.
Yeah. So there are sort of a few refinement criteria that we implement. One of them is just like, does the axion wind around 0 to 2 pi? Because that's what gives you a string. But right, the other thing you might worry about is if the axions are shooting off high frequency modes, do those high frequency modes escape your refined region, get to the coarse region, and then make things blow up? So it's also easy to implement like additional criteria that basically say if your gradients, because we get the gradients and Laplacians of these fields sort of for free as we evolve. You say, okay, if the gradients get too big or if the Laplacians get too big, let's just track those locations also. So in much the same, yeah, so we track both strings and high frequency radiation that comes off of them. We actually do it we do this, we were sort of want to be very careful. So we track it in the radial mode, but we also track it individually in the different components of the PQ scalar. What defines too large? Yeah, so this was a little bit phenomenological, but basically what we said was if you, we compare the size of the Laplacian of the gradients to basically the typical field values at the time of the simulation. Or at the time that we're deciding whether or not to refine. So it's not direct. It's not exactly saying like, oh, I have lots and lots of wiggles. It's saying if I have lots and lots of wiggles, I of course have a large K, and that should make the gradient at that location big compared to typical field values. So I agree it's worth thinking about more, but on some level, it is okay because we've convergence tested this in that like increase the resolution criteria for the high frequency modes, and we can see that like things stay the same. And also we've decreased it to the point that like our simulation explodes in numerical noise. And actually, it's quite easy to reach the regime where you explode in numerical noise. And the reason is you are doing some interpolations over the coarse fine boundaries. So if you have some high frequency thing that hits the coarse fine boundary, then you do some crazy interpolation on this high frequency thing, and you have a huge field value in the coarse region, and then again, it explodes. Yeah, it is a little bit nice in that like these, doing wave dynamic simulations, which these really are, it's just two coupled waves. It's easy to see when you've done something dumb, because by the time you've looked, your simulation is meaningless. Yeah. So cool. Let me just show you sort of a picture of what this, or it's not a picture, it's a video. I'm proud of this, of what this adaptive mesh refinement looks like. So here, what I'm showing you is this panel here. I'm sorry for the people that may or may not be able to see me indicated. So the left panel is a 2D slice through the axion field. So it's just the phase of this complex scalar, and it's winding between minus pi and pi. Now on the right two panels, the top one is a little zoom in on the axion field, and that zoom in is located within this yellow box that's in the large panel. So the top panel is the axion field in the zoomed in region. The bottom plot is the radial mode field within that zoomed in region. So I'm now going to show you what this evolution looks like. And my box is actually tracking a string. So that's where we're zoomed in on a string core in 2D. All right, nice, more or less smooth field. And now I'm going to zoom in and show you how good of resolution this AMR approach gets you. You can't even see the little yellow box in there anymore, but you can see in these zoomed in panels, string cores are still doing what they will. And yeah, I guess that's out to log equals 8, which is basically comparable to what these simulations that I was citing previously for you were getting to. Okay, so just like this quick summary here, you can get a big improvement by using adaptive mesh refinement, because the regions in your lattice that you need to resolve are basically 1D objects, which means if you take an adaptive mesh approach, you just refine along those 1D objects, and you effectively convert your 3D problem into a 2D problem. Now in practice, you have overhead and things that make this a little bit more complicated than dimensional reduction. And you get about a 1,000-fold improvement in the simulation volume that you're able to hold in a sort of standard supercomputing cluster type context. Great. So we sort of, we took two approaches, and in this simulation that we did. We wanted to get a larger dynamical range, which is just going out to larger values of log MR over H. But we also wanted to test like, what are really the resolution criteria that are relevant for this problem? Because the typical approach that people have taken in doing these simulations is to say, you only need MR, the radial mode mass, which is like the string width, times delta X, so your resolution, to be less than 1. So these simulations before us have been run out until you only have one lattice site per string width, and then they end. And that could be totally fine, but you also might worry that maybe one lattice site per string width is not actually a sufficient resolution criteria. So we wanted to look at that also. So the way we sort of leverage our increase in simulation volume, which is really, you should understand, as like more effective lattice sites that we can hold in memory, is to increase the minimum resolution of strings by a factor of 4. So at all times, we have at least 4 lattice sites per string width. And we also are able to go out to a larger value of log MR over H. So previous simulations got to 8, and we're going to go out to 9. What this plot is actually showing you here is what does our effective resolution look like as for these strings. And what's happening here at these like jumps, these discontinuities, is we add a new refinement level. So what we say is we evolve until we hit our minimum string resolution requirement of 4 lattice sites per width. Once we've gotten there, we say, all right, it's time to add another level. And we do this 5 times. So we start out with a lattice that's 20,048 cubed lattice sites at the coordinate sys level. But at the sort of late time, what you would need, you have effectively a 65,536 cubed lattice. That's the end result. But of course, I also want to point out that we are able to do some systematic checks just by sort of matching the previous approach and running out till you only have one lattice height per string width by just not adding refinement levels in the simulation. Cool. So let me show you what this looks like.
That's a super good question. What's going on there at that last level where you're dipping below 4?
Yes, we had not originally planned to go out to we were initially agnostic about whether or not we would go out to log 9. And the reason was we didn't know what the strings in our volume were going to look like. And of course, if we had looked at our box at log equals 8 and said there are no strings left here, it would not have made sense to evolve this out to log equals 9 because our interest is in studying the string emission. So in the process of deciding whether or not we were going to stop at log 8 or run out to log of 9, we misaligned when we wanted to add the refinement step, and we dip a little bit below 4 lattice heights per string width, but I don't think in an appreciable way. I think it's at 3.8. Cool. So let me just show you what this looks like in the simulation. So here's a 3D animation of the strings, these thin little yellow things evolving in the entire box, although I apologize, it's a little bit hard to see here. Cool. So the first thing we wanted to check, given this approach that's given us a larger dynamical range, but also better resolution, is like Giovanni and Marco, do we see an increase in the string length per Hubble? And indeed we do. We see a growth in the string network length, which is this parameter xi, that's basically, that's consistent with linear growth in the parameter log mr over h. So that was nice to see, and this seems to be more and more of a consensus feature in these simulations. The really interesting question is, what does the spectrum of radiation look like? So here I'm showing you these strings now, and they're radiated off axions, which again are a little bit hard to see, so let's just keep moving. Maybe this one is a little better. So this is a zoom in on a little box, and there's strings evolving here, and the shaded blue is radiation of axions coming off of these strings. So really our goal is to just quantify what that radiation looks like. Cool. So the way we do this is we look at our field state at a particular time, and we use the field state to construct first the axion energy density field, and then we construct basically the differential energy density in axions as a function of their co-moving wavelength. And just by appropriately differentiating this, seeing how this energy density is evolving, you can see like how much axions are getting injected into your system by all of the interesting PQ dynamics that you're simulating. Okay, so this is sort of what this differential spectrum looks like as a function of the axion wavelength. And the point here is we're just going to take a power model to try to fit this and ask what is the Q, like that quantity we were talking about before, associated with the emission that we observe. And here, you should look at the gray and the black lines. These are sort of the fiducial analyses, the windows in K over H that we use to fit. And I'll tell you now that this fit is actually really, really well described by Q equals 1. And just to sort of summarize, what does this look like over the course of the full evolution of our simulation? We look at Q between logs of about 7 and 9. These are plotted in black with some associated error bars. And what you can actually see is they seem to be constant right around 1, although the statistical uncertainties are admittedly large. Why do we pick 1? What do you mean? I didn't pick 1. I mean, I fitted it. So it's the number is like 1.01 plus or minus 0.04 if you fit to a constant index fit. Yeah. Yes. Yeah. So So it is fair to say that this is, because the error bars are large, we're only able to put sort of under 2 sigma tension. So like if we compare to what Marco and Giovanni have, that's in this dashed line. And what we see, yeah, is about 2 sigma in tension with that index evolution. But it is true that it would be nice to have smaller error bars and you know, if that is a tension, to push that tension to a more convincing level. I mean, the interpretation here is it is consistent with being constant, and we find no evidence for the growing index. Why of course, the statistical errors are large, in part because we only do 1 simulation. So yeah. Why did we pick 1? Yeah. Yeah. But oh, good. So this band here is showing you the 1 sigma error on the fit that we've done. So I mean, I guess we're telling you it's, you know, between 0.97 and 1.05. I guess I don't understand the. Well, there are bars. I'm fitting a constant value. That's true. Sorry, say that again. Right. Yeah. So this is the interpretation for. I see. Yeah. Good. Right. So there could be, and so the result we have is basically 0.1 plus or minus 0.05. So like it's consistent with 0. It's not excluded. I mean, that's certainly true. I mean, the benchmark I'm trying to provide to you then is if you take my data in black and you compare it to the fit from Marco and Giovanni's paper, then you would say those like that fit and this data are in about 2 sigma tension. But that doesn't, I know. It doesn't exclude the possibility of running. It's, yeah.
Yeah, there was a question by Giovanni or not?
Yeah.
Okay, go ahead.
Yeah, so yeah, I wanted to comment on this point because first of all, with only 1 simulation, I'm not sure you can confidently estimate sigmas. When you say there is 2 sigma tension or agreement, how you want to call it, I'm not sure that's sigma. I mean, I will not attach a real statistical meaning to that sigma. Because with only 1 simulation, I'm not sure you can really estimate systematics due to especially lead time.
That's true. It is hard to estimate systematics from a single simulation. We would like to do more. I mean, right. The reason we haven't done more is until yesterday, we didn't have any more computing time.
No, I understand that.
Yeah, but we have more computing time now, so we're gonna do more of these.
That's good. No, also because in our case, when we were only taking single simulations, we had some of them were consistent with Q equal to 1, like you see, but then only averaging over hundreds of them, we saw evidence for the increase of Q. And also, if remember from your paper, if you change the parameter of the fit, you could have a better agreement with ours result. Or so.
Yes, although
I would say that it's fair to say that at the moment the precision with only 1 simulation, statistical precision, is not good enough to tell, right, if really you see Q constant equal to 1 or growing or even decreasing. Because it's enough, right? It's enough, even 1.5 sigma, even 1 sigma of your slope, to that if you extrapolate that, you'll get very different results for the band side.
Yeah. I don't disagree with you. I don't think this is the end of the story. I think there are, I think this is I find this physics result interesting. I think it's definitely true that there could be unquantified systematics by merit of only looking at one simulation, and that you should do more simulations. I think you also get insight from, going to larger logs and also maintaining a higher resolution of these strings that are really only possible with AMR. And I think to that effect, this certainly is valuable.
Okay, before you continue, I have a question about before part. Do you know what really happens when high frequency mode cross meshings?
What do you mean? I'm sorry, I don't.
Sorry, imagine that the string in the core produce some high frequency mode.
Mm-hmm.
As it evolves, the wave, it will cross the different meshing regions.
Yep, that's true.
Do you know what happens when these waves pass through? The energy associated to it is just lost, or they bounce back?
Yeah, good. So you can have losses, and the losses are going in energy, and those will be associated with when you sort of are crossing into a coarser refined region, and your coarser refined region resolution is really sort of marginal for the resolution that you would need for these high frequency modes. Mm-hmm. That is really in large part what motivated us adding additional refinement criteria for these high frequency modes that tracks them as they evolve through the lattice.
But so can you check how much energy is lost overall in the simulation? Because, for example, from our simulation, we are seeing that most of the energy emitted by the strings were in high frequency region. Mm-hmm. So if this energy is lost, does it mean that your simulation lose most of the energy, or?
I strongly suspect this is not a large issue, but it would be something that it's not something I've checked in detail. So it's something I can get back to you on.
Okay, thanks.
Yeah. All right, great. Okay, so then I think I am more or less out of time, but I briefly want to say, if you take this index measurement of Q of about 1, 1 plus or minus some value, you can use this to make a prediction for the late time axion abundance, and then dial into a axion mass that you would predict about 40 to 180 microeV, which is certainly a wide range that is reflecting these existing uncertainties in the Q associated. Yeah, but Q being constant is an interpretation of the results that it is consistent, and you could, yes. I mean, I guess I don't have the axion mass prediction for that scenario here in these plots, but yes, it could be done. Yeah, I mean, this is the statistical uncertainty associated with the interpretation for Q equals 1. And no, I agree. There's a larger non-statistical uncertainty you could associate with not being able to determine whether it is a constant fit or a logarithmically growing quantity. So I mean, so one reason we are somewhat skeptical of the log growth is when in the test that we do where we reduce our string resolution, we do find that we observe a growing index for the emission spectrum. And that growing index then disappears as we maintain our high resolution, which gave us a non-statistical reason to think that perhaps the growing index was associated with some resolution effects.
I'm sorry, can I?
Yep.
Because it seems to me that even in even in the case where you have a finer resolution, you're still compatible with the slope that we find.
There's maybe marginal.
Well, I think that if you well, in one of your tables, if you are even more conservative than what you have been in the choice of the UV cutoff for the fit, you find the 1 sigma agreement.
Yes, there are systematic variations that we show that are sort of all within 1 sigma of one another, which is, I guess, what you'd expect for making small, unimportant changes in the way that you're doing the analysis. Like, again, I'm not claiming that this excludes a growing index. I'm saying the data as observed does not call for a growing index. So it's certainly true that you could add this to your interpretation and you'll have a largely unconstrained growth. And that is fair and true, but
yeah, I don't know, because if you really want to, unfortunately, if it's really true, right, that the Q is 1 and it doesn't depend on time, then in order to prove this statement, you really need
you need a lot of simulations.
A huge precision, right? Because you need to be 1 within 1%, within 1 over log, which is 70. In order to avoid. So unless you have such a precision, there is no evidence that Q is equal to 1.
I don't understand how my...
Huh? Because this is basically the conclusion will be like the conclusion of our first paper, where we said that we didn't have enough precision to measure Q, and Q can be larger than 1, smaller than 1, or equal 1. Until one has enough precision to discriminate the 3, we cannot conclude anything, right?
So I guess the question is, Giovanni, if you had opened up your simulations and you had seen something that was consistent with 1, would you have added the linear term to your fit?
This is what we found in the first, in our first simulations. And we still concluded that with not enough precision, we cannot arrive to a conclusion. So we had to allow not to be conservative and say that we don't know if Q is larger, smaller than equal to 1, unless we have enough precision to discriminate which one is at log equal to 70. I think this is the only conclusion one can draw.
Yeah, I mean, we can argue about whether or not you can add unconstrained parameters to your interpretation and then extrapolate large uncertainties. I don't know if we're going to come to a meaningful or a satisfying resolution to that argument. I think, like, if it makes everybody happier, we can sort of contain this as this is a simulation. This is a result interpreted within the context of a constant index fit, which maybe has, Nico, I don't think is here today, but there are some people, oh, yeah, he is. There's some people that would tell me Q equals 1 is perhaps a theoretically preferred index for my emission spectrum. And here I am performing a simulation and interpreting within that model. I agree. We should do more simulations. I am very interested in hearing what you think might be convincing or as systematic checks or improvements to make in these simulations. But I'm not, if we agree that there isn't sort of precision, there's just a matter of interpretation. And if we choose to interpret things differently, I'm not sure what we can do about that.
No, if you had much more precision and you could exclude at several sigma our slope, so you say is Q is 1 plus or minus 0.05, 0.01.
Yeah, I'm not sure this is,
well, unfortunately, that is what it takes.
Can you remind me how much resolution is your simulation is better than Giovanni one?
So it's 4 times higher string resolution.
No, but in total. Like if they want to do the same resolution as you.
It would be, I guess, 512 times larger number of lattice sites.
Okay, so you will need to do less simulation than them to because you have more resolution.
Well, so it sort of depends on whether your dominant uncertainties are sort of from field realization to field realization as you evolve them, or if these uncertainties are more statistical in nature within a particular realization that you can then average down.
And other question that because I was you read both papers and what are there's some difference between initial conditions, right? Can you comment about the your initial conditions?
Yeah. So I can say a little bit about that. So the way that we set our initial conditions is that we start in the unbroken phase of the theory with some thermal initial conditions that we evolve through the symmetry breaking, and then we just get our topological defects and our field configuration dynamically. And now, if I've understood the approach that's been taken by some other simulations, it's been to start with an initial configuration and to evolve it in the broken phase, and then to sort of rewind the clock and say, nope, this is actually the beginning of a simulation at earlier times. And I think maybe one of the things that's valuable about the approach that we're taking here is that at all times your strings have realistic widths, compared to if you've rewound the clock, your strings have effectively the wrong width for the time that you're simulating at, and you might worry about dynamics that's associated with your strings being unphysical.
There is another question on Zoom, but Bodo, please.
Yes, hi. Kind of in the same direction. I understand that you calculate the power spectrum only on the coarsest level.
Yep.
Do you have an intuition of how much error this will additionally give to the power spectrum?
I don't have any intuition for that, and that's something we're going to be checking in simulations 2 through 10.
Okay. And then could you check that by just running higher resolution simulations, but mainly for basically for the first few logs, or for the first from log 6 to 7 or so, with a higher resolution, and then
that could be done. Although I think it's it's still an appreciable amount of CPU time to get to 6, right? Mm-hmm. If we got to 6, we'd probably just want to go all the way out to 9 or 10 anyway. So no, it's something we're checking. I don't have a strong answer for that right now.
Okay, thanks.
Davide?
Yeah, thanks. Thanks for a nice talk. And I have a broader question that is maybe also for Giovanni. It's about this approach in general. So the adaptive mesh refinement, could it be actually an interesting way forward, or does it have some systematic limitations related to the resolution of the high frequency modes and so on that ultimately may make it not really reliable? Like, what is your take? Could this be the future with more simulations to really tackle this issue, or should we?
Yeah, this doing AMR is not going to get you to log equals 70. So like the simulations that we did here, we used 5 million CPU hours and 10% of NERSC, which is the government supercomputer at Lawrence Berkeley National Lab. So like it is doing these simulations, like even to the sort of limited dynamical range that we have right now, takes up an appreciable fraction of the resources that are in theory available to you. And of course you're competing against, you're trying to make a log large. So normally you might say Moore's law will save me, but Moore's law doesn't save you from trying to make the log of a quantity large. I think it's certainly true that AMR is probably a very promising way of pushing forward what dynamical range you can have. AMR is a tool that is widely adopted in fields that are not particle physics. So, the code that we used was originally being used by people who study fluid flow on the Earth through oceans and rivers and that sort of thing. People who do numerical GR use AMR type approaches. It's like it's like fairly old. It's like a 30, 40-year-old technique, and it's been fruitfully applied in other fields. I think it's a little bit hard to code up and get working. So like if you're a particle physicist and you want to build something that like you can build by hand and understand, it's going to take you a long time. And we were lucky to have some very good collaborators from the exascale computing group at LBNL who got us set up on a very nicely established code framework that has been used in a lot of different contexts. And I think, on some level you can trust what these people have done. This is their careers, and it's sort of a well-accepted technique for PDE problems broadly. There's no reason not to use it here or really in other contexts in physics where you might need to do sort of simple, but like classical field dynamics.
Okay, thanks.
Can I say something?
Yeah, yeah.
No, I just wanted to say that there is some problem with initial conditions, in the sense that the initial conditions are actually the bottleneck of these kind of simulations, in particular for this case, which is the physical case. So the initial conditions, at least those that you show, have the size of the core, which is much different than the typical size where the radial mode should be over the MR if you want. So essentially, you're essentially exciting the core of the string, at least in the video you showed initially. And it is known that there are some bound states on the string made of radial modes, and these are long-lived and emit ionergetic axions. There's some literature about these bound states of radial modes in the string. This means that if you essentially don't fine-tune the initial conditions such that the string core is exactly MR or something of order MR, then what you see in the spectrum is not the emission of radiation from the screening regime, but is the emission of radiation from the excited states in the radial the bound state of the string. And this completely ruins the spectrum, and that's an issue that we essentially dealt with for probably 2 years, to try to fine-tune initial conditions in such a way that these long-lived excitations disappear, which they will disappear in cosmological constant, but this is not a cosmological constant context, is a very idealized Fewy-folding context. And for this reason, doing these fast string simulations would helps, because essentially there's more time in these fast string simulations for these excitations to disappear. So one of the most important things to maybe think about is changing the initial conditions in such a way that you have the right core size initially. That because those essentially contaminate the spectrum and change completely the spectrum compared to what should be physically in the large log limit. That's the.
Yeah. Okay. That was a long question statement, and I'm happy to have a longer discussion about it later.
Yeah,
but I don't think I've had quite the time to digest what you're saying.
Perfect. Time to conclude then.
All right. Well, thank you everybody for your attention.